In this video, I'll be going over a question related to the learning outcomes. Explain and use the principle of superposition of waves, and explain experiments that show diffraction and interference. This question comes from ACE Physics Syllabus Code 9702, Paper 21, from May-June 2011. Question number 7. It reads, explain the term interference. Well, interference is when waves meet. And I'm going to use the word superpose. When waves superpose, which is the same thing as meet or overlap. When waves superpose, we apply the principle of superposition. So I chose the word superpose to remind myself that I'm applying the principle of superposition, which says what? The resultant wave is the sum of the individual waves. So when waves add up, they can add up and reinforce, like crest meeting crest or trough meeting trough, or the waves could add up and they could destructively interfere. Crest could meet trough. You want to try to avoid using the word interference if you're explaining the term interference, and so sometimes we're tempted to go right to the ideas of constructive and destructive interference, right? So we really have to kind of think about what that really means. When waves add up to reinforce and cancel, we observe a pattern known as interference. All right, the question goes on to read, a ripple tank is used to demonstrate interference between water waves. Describe, 1, the apparatus used to produce two sources of coherent waves that have circular wavefronts. Well, they give you some space here, conveniently enough to perhaps draw a sketch as best you can. And I'm not the best artist, but I'll do my best to sort of draw this apparatus. And then I can support my sketch with some description here in these lines. So a ripple tank is, we got a tank of water. And so we're going to sort of look at this from the top down. But this whole thing is like a tank that's filled with water. And on one side of the tank, we would want to place an oscillator. And that oscillator would be connected to two spherical dippers that can sort of bob up and down in the water, and they'll displace the water here. That will be the disturbance. We need them connected to the same motor so that they oscillate at the same frequency. Really, our job here is to describe how we're going to achieve this coherence. And so one way is to connect two spherical dippers to a single oscillator, and they're going to oscillate. And so the circular wavefronts are going to kind of propagate out like this, and they're going to meet along this part of the ripple tank. You can see the question goes on to say how the pattern of interfering waves may be observed. And so we'll see the interference pattern sort of in this part of the tank, or especially along sort of the edge of the tank here if we're trying to actually look for the displacement, where there might be a point of constructive interference, say here, and we'd see a lot of splashing, and then points of not so much splashing. That's where we see the cancellation, right, where there's destructive interference. You can kind of look on ahead of this question and see, well, this is exactly what we want here. It says a wave pattern produced in B is shown in figure 7.1. And so here would be the sources of the circular wavefronts, and then that's the interference pattern. So that might give you a clue as to how to approach this question if you needed to. Sometimes it's helpful to sort of preview where we're heading with this. And so these waves are going to send out these circular wavefronts, and eventually they're going to sort of overlap, right, in these areas, and that's where we'll see points of reinforcement, constructive interference, or points of cancellation, destructive interference. And so we'd observe the interference kind of over here. So describe the apparatus. So we have a tank of water with two spherical dippers connected to the same oscillator or motor at one end. All right. And this is just sort of the way that I would say it, but you would always want to kind of go through and take a look at the slides and go through the reading and then think about how you would sort of put this in your own words. This is just an example of what I would say. There's another way to sort of achieve this interference pattern here in a ripple tank, and that would be to use a single sort of paddle-like oscillator. All right, and so we'd still have this, connected to our motor here, and it'd be more of like a longer paddle type oscillator, and it's going to send out these plane waves. If we then constructed a barrier that had two gaps in it, then we know what's going to happen when a wave goes through a gap or a slit here, an opening. It's going to spread out, it's going to diffract. And so here we're going to sort of achieve the same thing that we get with the two spherical dippers bobbing together in the water. We're going to send a single wave, and so there's a single wavelength and therefore frequency here, and each of these diffracted waves that emerge here will have the same frequency also. We'll see the same interference pattern sort of in this part up here, right, where there's points of constructive interference and points of destructive interference. How will that pattern of interfering, it says, describe how the pattern of interfering waves may be observed. Well, we need to kind of, in a ripple tank, sometimes you'll see this with like a lamp and an overhead projector, and so it's sort of displayed, sort of on a wall. But we need some way of sort of illuminating this, and so the crest of the wave in the ripple tank, if there's a light shining on them, then the crest will appear brighter. And so we'd notice where the waves are, crest is meeting crest, we'd see an even brighter spot there. And so we'd need a lamp to illuminate the crests of the waves, and a slow motion camera to observe the waves more clearly. All right. So some means of being able to stop or to slowly sort of observe the pattern there, so you can see those points of reinforcement and those points of cancellation. And again, it is that repeating pattern of places of reinforcement and cancellation that is the characteristic interference pattern. The question goes on to read, a wave pattern produced in B is shown in figure 7.1. Solid lines on figure 7.1 represent crests. On figure 7.1, 1. Draw two lines to show where maxima would be seen. Label each of these lines with letter X. And then draw one line to show where minima would be seen. Label this line with the letter N. So I've got handy right here my clear plastic ruler. And if we look sort of directly in between the 2 point sources that are sending out these circular wavefronts, we can see that crest meets crest right there, right? And so sort of the first wave ends up actually meeting the second wave right here, right? So see how this all the successive waves from, say, this source here are this one, this one, this one, 4, 5, 6 waves. 1, 2, 3, 4, 5, 6 waves there. So we see sort of 6 wave fronts from each of these sources. If we look at the first, second wave from this source, we can see that it intercepts the first wave here. And then there's these points that sort of go all along right here, right? And so where the second wave and the second wave have met here, the third wave from each one have met here, fourth, fifth, and the sixth wave. They're all meeting together sort of along this midline in between the 2 point sources. Because each of the waves have had to travel the same distance, right, to get to this midpoint, we kind of know that that's going to be a point of constructive interference where crest would, meet a crest. And so you can kind of see all along that line there where that's true, where crest is meeting crest. And so that would be a line that I would label X, because it would be a point where there'd be a lot of splashing in the ripple tank, right? So maximum. You can kind of see with your eyes perhaps that there are all these places where this happens, where crest meets crest, and kind of along these lines here. There. Now, because the question asked me to only show 2 lines, that would be sort of where I would stop. But for the purpose of the video, I will show all of the possible answers, just kind of with a dashed line here. You can see that there's a point along there, a line along those points rather. In there. Right? And so you can kind of see where all of these crests are meeting crests there. Now, by the time you get out here, you can see that this wave hasn't had time to sort of make it all the way out there yet. So we can call these like X prime possible answers that would be just as correct as, so any 2 of those lines there for part C, question 1. Now, one line to show minima, I would just look for one right in between my 2 X's. And so here we can see that, for example, there's a crest from that wave, but it's a trough. It's in between these 2 waves for this point source. And so this would be a point of destructive interference where, yeah, there's a crest from that wave, but it's meeting up with a trough from another wave. And so when crest meets trough, that's going to add up to 0, and so very little splashing. And so all along this line right here, that would be where minima would be observed, not so much splashing.